Так, ну хорошо, Леша, ты с командой когда начинать?
Командую.
Ага, все, пора. Okay, so I'm going to speak about Cactus group and monodromy of Bete vectors. So my main example will be Godin model. Attached to any semi-simple Lie algebra G. But in principle, I believe that with appropriate changes, this works for a wider class of quantum integrable models. So maybe I'll have time to discuss the generalization of this to the XXS Heisenberg spin chain. Now, now let me just formulate the question. So in the Godin model, we have many commuting Hamiltonians that are linear operators on a tensor product representation of the Lie algebra G. So suppose we have a collection of highest weights of the Lie algebra G. Then we can take the corresponding irreducible finite dimensional representations and tensor up these representations. This is the space of states. For example, if G is SLN and all the lambdas are the first fundamental weight, then this is just the nth tensor power of the standard representation Cn. So originally, Godin considered this for SL2, and this was 2 to the power n dimensional vector space. Okay, then what are the Hamiltonians? These are the following pairwise commuting operators on this space, depending on a set of pairwise different complex numbers. And these are the following operators. So basically, this is what you get if you take the Knižný-Zamolodchikov equation and remove the differential term. So this is a coefficient of dzi in the kz equation. So omega ij is the usual Casimir operator. So here xa is some basis of the Lie algebra G. X upper A is the dual basis. With respect to the to some invariant non-degenerate form on G. And so for any X, for any element of G, I denote by X to I, the element just X in the ith copy. Okay. So these are some operators acting on the standard product space, and it is relatively easy to see that they pairwise commute for any given collection of CIs. Then, as usual in quantum integrable systems, the following diagonalization problem arises. So we want to construct some eigenbasis for this, joint eigenbasis for these operators. In fact, the first observation is that all the omega ij commute with the diagonal action of G. So in fact, we'll solve the diagonalization problem if we diagonalize these operators in the multiplicity space. So it is sufficient to diagonalize this to diagonalize HI in any home space or any space of highest vectors in the tensor product. Let me denote it like this: V of lambda underline mu. So maybe upper mu. That is and weight of because this is because the tensor product space, we can decompose it with respect to the diagonal G as this, and since all the omega ij commute with the diagonal action of G, they don't act on the second factor and act only on the first factor. So the diagonalization problem is actually in these spaces. Now, what is the method for diagonalizing? So let me give an example. So that is called Bete-Ansatz method. So I assume that everybody or almost everybody have heard of Bete-Ansatz, and so I just recall the version of Bete-Ansatz appropriate for Godin. So so we are looking for the eigenvector in particular form. So this particular form is in general it is a bit complicated, but let me just and I don't really need it. So let me explain just the example of SL2. If G is SL2, and then we are interested in the eigenvectors of the following form. So let P0, maybe P lambda underline, be the highest vector the tensor product of highest vectors of all the V of lambda I. That is P lambda 1, tensor so on, tensor V lambda n. Then the idea is to, so this vector is of course the eigenvector for all these operators, and actually it is an eigenvector for all omega ij. So the idea is to apply to this vector some lowering operators depending on additional parameters, and write an algebraic equation on these additional parameters, guaranteeing that you get an eigenvector. So consider the eigenvector of the vectors of the following form: f of W1, W2, so on, f of Wk applied to this vector V lambda. So this is the theorem. So for SL2, I think it goes back to Godin, that this is an eigenvector for all the HIs altogether, if and only if the following the following system of algebraic equations is satisfied. For any m from 1 to k, we have sum of the i's over ci minus wm minus we have this system of algebraic equations. So in the case of SL2, lambda i's are just numbers, and beta ansatz vectors have this relatively easy form that they are obtained just by successive applying just some operators successively to the highest vector. So here, this f of w is just the sum of f I over w minus c. So, any questions on this? Okay, so then let me formulate the problem. I'm addressing here. So first, let me note that this generalizes. So this set of beta ansatz equations and the beta ansatz vectors, this can be generalized to any semi-simple Lie algebra with appropriate changes. And this problem is general. So the problem is that you cannot solve these algebraic equations explicitly. And in fact, in the first non-trivial examples, we have the solutions are not rational expressions of CIs, rather they are, well, just solutions of some polynomial equations whose coefficients depend on the I polynomially. So we have a non-trivial algebraic extension of the field of rational functions of C1, Cn. Or equivalently, if we view these solutions to beta ansatz equations, all the Wm's as functions on Z1, Zn, they are multi-valued functions. So the problem is, algebraically, to describe the Galois group of this extension, or geometrically, this is the monodromy group of these multi-valued functions. Okay. So the question is, what is this monodromy group in chain? And what we have some partial answer to this question. Namely, we can describe explicitly, as much explicit as is possible, some understandable piece of this group. And this understandable piece, I will explain that it is in some examples it is the whole Galois group, but anyway it is large enough to be interesting. So we can describe. So this comes from the following. So geometrically, this means that we cannot describe the monodromy over all possible loops in the parameter space, but can describe explicitly some of them. So that is describe the monodromy along some particular loops.
Do we know like a full answer for some cases when, for example, lambdas are fundamental or something like that? Or
yeah. So so there is a complete answer for for almost all cases when lambda, when the group, when the Lie algebra is SLN, and the representations are just standard representations. Then this understandable piece covers all or almost all the Galois group, the whole Galois group, and this is because by some simple reason, because this understandable piece is already the at least the group of all even permutations of the Bete roots. So it cannot, the Galois group cannot be bigger. It can be all permutations, but not bigger. Yes. So in general, the difficulty is that at least naively, what is the parameter space? So the parameter space is Cn minus the diagonal minus this arrangement of hyperplanes, and naively the monodromy group should be just some quotient of the braid group, which is the monodromy, which is the fundamental group of this thing. But in fact, this is wrong, because our solutions to Bete equations can be ramified at some extra points. So in fact, they can be defined in such a way that they are in general not that they have no ramification at this divisor, but they have ramifications at other places, and it is difficult to describe the ramification divisor. So the idea is to describe some sufficiently large locus in the parameter space over which we are guaranteed that these functions are unramified. And so to do this, and so doing this requires some work. So let me pass to this. So In fact, what I am going to do, I'm going to first to describe some natural compactification of the parameter space, which still parameterizes some family of pairwise commuting operators. And
so can you explain what the problem can be with this parameter space on some simple examples?
Yes. So the yeah, okay. So the problem can be the following, that there are some particular values of these complex numbers such that the operators hi of this C1, Cn are non-diagonalizable. So sometimes it is possible for them to have non-trivial Jordan blocks. And this means that at such a point, for such a value of C1, Cn, some at least two joint eigenvalues come to the same, and this means that the multivariate function has a ramification at this point. Okay.
Okay.
Yeah. So so this corresponds to ramification of the joint eigenvalue, or of some of these guys. And so in fact, two different patterns as vectors come to the same. Yeah, and but on the other hand, this never happens when the operators hi are self-adjoint. With respect to some Hermitian form. Because if self-adjoint operators are always diagonalizable, so we don't have this. And this is actually the idea. So restrict to such a locus where these operators are always self-adjoint. Now the theorem is that well, for real values of parameters, these operators are always with respect to the standard, just to the tensor product of standard Hermitian forms on the factors. Of invariant of invariant with respect to the compact form of the group G. Which is SUN or G equals SL. Okay, so this means that that at least on the real locus, we're guaranteed that that the Godin Hamiltonians are always diagonalizable. So we have no ramification. So this is the good news. The bad news is that this real locus, if we look at the parameter space naively, just as the complement of hyperplanes, so the real locus of this complement space of so problem Rn minus the diagonals is disjoint, is a disjoint union of contractible sets. So this disjoint union of cones which are all contractible. So there is no interesting fundamental group there. So we cannot get any interesting monodromy from restricting to just real values of the parameters. So I'm going to explain that in fact this leads to some interesting monodromy group if you consider the natural compactification of the parameter space, which still parameterizes some integrable models. So we can extend the parameter space to its compactification, and it will lead to something with interesting fundamental group. So for this, let me give an example. First, so let's consider an example. So let G be just SL2, and let N equal 3. Then we have operators HI, but in fact we always have the following relation on them, that sum of all HI is 0. So there are actually not 3 of them, but 2. And moreover, the sum of Zi times Hi is always the same. It is always just the sum of omega ij for all I non-equal G. So it is up to some constant, it is just the diagonal cousin. which acts by constant on due to Schur lemma on any highest vector space I was considering. So it is still not interesting. So this is the first. So this is actually the first non-trivial case where we have, apart from this and this, we have one non-trivial operator which can be chosen as just H1. This is omega 1, 2 over Z1 minus Z2 plus omega 1, 3 over Z1 minus Z3. So I am interested. So here I am interested in this case. I am interested in diagonalizing just this operator, just this single operator. Now let's consider what happens in the limit when Z2 Z2 and Z1 become infinitely close. Z1 minus Z2 close to 0. Okay. So then what do we see? We see that the second term is bounded, and the first term goes to infinity. So this means that if we renormalize, so the H1 itself doesn't have any limit, but if we multiply it by Z1 minus Z2, it becomes just omega 1, 2. And this is it's still some reasonable operator. So and similarly, when C1 minus T3 goes to 0, we get just omega 1, 3 in the limit. And when Z2 minus Z3 goes to 0, we get just the limit of H1. It is fine. It is finite. So we get omega 1, 2 plus omega 1, 3. Maybe still multiplied by Z1 minus Z2. And subtracting it from so this diagonalizing this operator is the same as diagonalizing the operator omega 1, 3 or omega 2, 3. Because their sum is already the linear combination I was writing about. So we have some well-defined limit when the parameters collide, when the ZIs collide. So, and moreover, in this space, in this case, the parameter space is actually one-dimensional. So what is parameter space here? So this is C3 minus union of Zi equals J. But in fact, the space of operators I need to diagonalize doesn't change under simultaneous shifts of the Zi's and under simultaneous deletions of the Zi's. So the original parameter space is in fact the quotient of this complement of hyperplanes by the actions of the affine one-dimensional affine, the group of affine transformations of the line. F1 C that is Z2 Z plus B. So this quotient is then just CP1 minus 3 points, 0, 1, and infinity. And the above limits are actually they actually explain how to attach a commutative subalgebra to all these 3 punctures. So this corresponds to 0, this corresponds to infinity, and this corresponds to. Okay, so then passing to the real locus. So we have RP1. So naively, when considering just the variables Zi taking real values as the parameters, we have RP1 minus 3 points, which is the circle with 3 punctures. But this limiting procedure explains how to attach something to these punctures to get a continuous family of integrable models. So we have something parameterized by RP1. And this RP1 already has an non-trivial fundamental group, so there may be a non-trivial monodromy around when we go around the circle. So this is an example illustrating that. So what I'm going to do. So for general N, so we can view the original parameter space again as the complement of hyperplanes divided by the affine group of the line. And this this quotient has a natural interpretation as the moduli space of genus zero curves with n+1 marked points.
But in case n equals to 3, we get
M04.
Okay. Yeah.
And this is just the projective line. So this is a modular space of genus zero curves with n+1 mark point. Mark points that are just d1 up to the n and the infinity, which is preserved by this affine group. So this is the same as just CP1 to the power n+1 minus over the just the group of projective transformations of the line EGL. So this identification means that I can put the n+1 point to the infinity, and then I still have the affine group of the line acting by symmetry. So I have to divide by the affine group. Okay, so this is the moduli space, and now the theorem. And goes back to Aguirre, Felder, and Veselo. That the family of spaces of commutative operators family of linear spans of the operators HI extends to the Deligne-Mumford compactification of this moduli space. So this M0 n+1 bar parameterizes all all genus zero curves with n+1 marked points that are possibly nodal. So we allow simple nodes. So the typical point of this space is something like this. So we have point infinity. We have several points ci. C1, C2, C3, Z4. So these curves can so this such a curve can be a union of irreducible components that are all just projective lines intersecting transversely at some points, such that this intersection graph is a tree, and on each component we have so these curves have to be stable. So this means that each of the components has at least 3 distinguished points, either marked points or nodes. So these nodes components projective lines, and yeah, so the linear Mumford compactification is the modular space parameterizing this sort of curves. And the topology of this modular space is determined by the rule. So when you have several points going to the same limit, when several points collide, they bubble off into a new component. So it turns out that it is possible to. So we have seen this on the example of n equals 3. That it is possible to extend the family of commutative subspaces in the linear operators in our representation to this compactification. So what we get, a vector bundle over the Deligne-Mumford compactification with the fiber being the span of hi's. So this is an n-1 dimensional vector bundles because there is a linear dependence on the hi's, namely the sum of all hi's is 0. n-1. So next, if we take all the joint eigenvectors in the given representation for these guys. So joint eigenlength, maybe eigenvectors up to deletions. in the space V of lambda for mu, we get a covering, possibly ramified, covering E whose fiber over a point of this Dillon-Mumford space is the set of joint eigenlines for the corresponding commuting linear operators. Okay. Once we extended the HIs to the compactification, we have such a covering over the compactification. Now the next theorem is that this covering is unramified over the real locus of the Dillon-Mumford space. And moreover, it turns out possible to describe explicitly the monodromy over this real Dillon-Mumford space.
What is it? I mean, is it like we should replace all these balls into circles or what?
Yeah. So this space, yeah, exactly. So in principle, there are several real forms of the Dillon-Mumford space, but for this we need just the most straightforward one, where we assume that all the marked points are real. That is, we just take the same pictures, but with the points sitting on the circle. Yeah, so this is the moduli space of cacti, because such pictures look like cacti. And since we are dividing by dilations of the line, so all these components, so all these circles have to be regarded as three-dimensional objects. So they are all these components up to are taken up to flipping, because multiplying by -1 flips everything on the given component. Yes. So yeah. This makes possible to describe the fundamental group, and more precisely, it is as usual. So you in fact you see the same effect when you are studying the fundamental group of the complement of hyperplanes. The braid group is much easier to describe than the pure braid group. So the actual fundamental group of the complement to hyperplanes is a pure braid group, but it is easier to divide this complement by the symmetric group X and there and describe the fundamental group of the factor of the quotient. And similarly here, it is easier to describe the fundamental group. So next section. So the fundamental group of the real Deligne-Mumford space M0 n plus 1 bar equivariant with respect to a sense is called the Cactus group. And it is possible to describe it explicitly in generators and relations. Namely, well, to do this, we have to select the base point of our topological space. So let's do this. So we select the base point, just some non-degenerate curve. Some parts, well, in fact, it can be any non-degenerate curve. Then we can take as the generators of the equivalent fundamental group. We can take the shortest paths connecting such non-degenerate curve with its image under the action of the symmetric group, with some of the marked points being permuted. Shortest path means that it intersects the boundary divisor only once. So how to picture this? We start with some with a non-degenerate curve. Then we pass through the boundary divisor. With several points going to the additional component, say from ZP to ZQ. And then we're saying that this point is the same as itself, but with the points on the additional components going in the reversed order. So ZP is here, ZP plus 1 is here, and so on. ZQ is here. And then we can deform it back to the non-degenerate curve with the points with the markings of the points being flipped. So we have ZP minus 1 here. The next will be ZQ. Next will be ZQ minus 1, and so on. ZP plus 1, ZP, and up to Zn. So ZQ plus 1 over here. So the shortest paths connecting connecting a non-degenerate point with some of its SN conjugates, intersecting the boundary divisor only once, are just flipping a segment, flipping an interval in the sequence Z1 to Zn. So let me denote this generator as SPQ. And I have such a generator for any interval from P to Q inside the bigger interval from 1 to n. So now the defining relations of this fundamental group, they were first described by Davis, Januszkiewicz, Scott. So all these SPQs are involutions. Next, if two intervals do not intersect, then the corresponding SPQ commute. So if the intervals do not intersect. And another relation we have when one interval contains another. If this, we can conjugate the smaller with the bigger. And we'll get S with respect to the interval conjugate to P to Q2 under the flipping of the bigger segment. Okay. So this is the complete description of the defining relations, and yeah, so we have already seen this. So anyway, it is easy to see that such a group surjects onto Sn with this surjection sends SPQ to the involution in the symmetric group that flips the interval from P to Q. So it does nothing to, it stabilizes all the points up to P minus 1. And flips the interval from P to Q. Okay.
So how can we understand the last relation? It's not clear to me. is it some?
The last relation. This means that so both of them actually have the easy geometric meaning, that the commutativity means that we can bubble off two intervals separately, and it doesn't matter in what order we flip them. So this is the first relation, and so this was the second, and this is going to be the third. And here we are saying that we can first flip some bubble off all the points on some interval, and second bubble off the some sub interval there. Then conjugating the flip of the smaller interval with the flip of the bigger interval is the same as just flipping the conjugate. So you can so I mean it is possible to draw several pictures like this, and see that it is that these two the loops the paths representing the left hand side and the right hand side are homotopic equivalent to each other. So the idea is that we can how to say it, that we have retract both the left hand side and the right hand side to some path passing through this point, passing through this deeper stratum.
What is known for these groups? Like some example for small n or something like that.
Yeah. So this group is always infinite, and it shares many properties with the braid group, which is also infinite surjecting on the SN. So the example when n is 3, so this is the first non-trivial example. Here we have just 3 generators, S1, 2, S2, 3, and S1, 3, such that all of them are involutions, and there is a relation that S1, 3, the conjugate of S1, 2 with the S1, 3 is S2, 3. So this is the only relation. So this means that we can take as the generators just 2 of them, S1, 2 and S1, 3. And there will be no relations on these 2 generators. So this is so in this case, this C3 is the group generated by S1, 2 and S1, 3. Just model the relation that they are both involutions. So this is a free product of so this is the free product of Z2 times Z2. Or it is the same as the semi-direct product of Z2 with Z.
Is it a consequence that this is a fine while group for SL2?
Oh, well, in this case, it is accidentally an affine while group, but in general, it is bigger. It is in general, it is not. So it is not isomorphic to any other natural group. But it can be described. In fact, it can be described. It is somewhat related to the braid group. So, namely, namely, there is a homomorphism which is conjectured to be an embedding, and maybe already proved to be an embedding into the modes of closure, modes of completion. Of the braid group. Namely, what is modes of completion? You can view the pure braid group as a pro-unipotent group.
Maybe can you explain what is a pure braid group?
Pure is the kernel of homomorphism of the braid group to the symmetric group. So the braids that do not permute the point. Okay, and so the pure braid group this braid group can be regarded as a pro-unipotent group, and then you can define an infinite dimensional Lie group such that the pure braid group is embedded there as a lattice, and you can extend this to the braid group itself. Then the cactus group is embedded into this infinite dimensional Lie group. In fact, infinite dimensional and factorial component Lie group. So for so maybe let me just illustrate what this embedding looks like. That you can. Roma is asking, are there analogs of the cactus for other types? Yes, of course. There are. You can take any wild group and do more or less the same by replacing, namely, the generators are assigned to any Levy root subsystems generated by some subsets of some maybe connected subdiagrams in the Dickinson diagram, and the relations are that they are all involutions. For disconnected union of subdiagrams, you have commutativity, and if one diagram is inside another, you have this conjugation property. And the homomorphism to the wild group just sends the generator corresponding to the subdiagram to the longest element in the whale subgroup corresponding to this subdiagram. Yeah. So and similar fact is holds here that cactus group corresponding to the wild group can be embedded into. Maybe I'm not sure it is proved to be an embedding, but at least it can be mapped to the Artin braid group corresponding to the wild group. So this embedding on the easiest generators is p plus 1. It does the following. It takes the so-called unitarized braid generators. Namely, you take the generator TP in the braid group, and just normalize it to make it an involution. Namely, you multiply it by the, or you divide it by the square root of its square. So the square of the generators TP of the braid group belongs to the pure braid group, and you take square root of this, not as an element from the braid group. So the square root is not TP. It is the square root in the unipotent Lie group. So it is some element from the multi-completion. So, and this is the image of the element from the Kepler. So this is how one is related to another. Yeah. So now, so why trying to keep this analogy with the braid group it is because the cactus group CN plays the role of the braid group BN in so BN acts by endomorphisms of multiple tensor products in braided categories, braided monoidal categories. So there is another version of monoidal categories with permutation symmetry that that has cactus group playing the role of the braid. This is called co-boundary monoidal category. So that is the following thing. This is a monoidal category. That is a category along with tensor product, such that along with the functorial isomorphism between tensor product in one order and tensor product in the opposite order. That is for any pair of objects, we have the morphism from X tensor Y to Y tensor X called commuter. Satisfying the following properties. So the first, it is contrary to the braiding, it is involutive. That is CXY composition with CYX is always identity. And next property is replacing the braid relation. So instead of braid relation, we have the following. We have two different ways of reversing the triple tensor product. We can either first permute the first two factors and then permute the product of the first two factors with the third one. So that is, we first take CXY tensor identity, and here we take CY tensor X Z. Or we could first permute Y and Z, and then permute X with the product of Y and Z. This diagram should complete. So this is identity tensor C by Z, and this is Cx tensor Y. So there are reasonable examples of such categories, which I introduce in a second. And the general theorem of Henriques and Kamnitzer shows that all the commuters on the n-fold tensor product x1 up to xn generate Cn action by automorphism. So we have so indeed Cn plays the role of the braid group, and it's in some other type of monoidal categories. And the main example of such monoidal categories is the category of Kashiwara G crystals. So this is roughly a combinatorial model of finite dimensional G modules of the tensor category of finite dimensional representations of the Lie algebra G, where the weight spaces, weight subspaces, are replaced by finite sets. So basically, we are modeling basis vectors in the weight subspaces by some elements of finite sets. We just consider the basis as a set, and the operators representing Chevalier generators EI, FI are modeled by maps between these sets. Yes, yeah, Roma, thank you. Yes, so by automorphisms, indeed, the pure Cactus group, that is the kernel of the map to Sn, but the whole Cactus group acts by morphisms between where this sort of tensor products in different orders. So if you sum up all n factorial terms and these objects over all the permutations, it is acted on by the Cactus group. That's right. Thank you for clarification. Yes. So so the operators representing EI and FI are represented by by maps between the weight set corresponding to mu and the weight set corresponding to mu plus alpha. So basically, what we are doing here is that we are maybe formal union with zero, because sometimes we want to annihilate some vectors and they should go outside. So basically, what we want to do, we want to replace all the take some bases and replace the operators by the maps between basis vectors. So it is possible. It is easy in the case of SL2, because we just have, for any reducible representation, we have just one vector up to proportionality in each weight space, and so we have several vectors marked by the weights of my representation, and they are connected by arrows representing the action of the operator F. Yeah, so now there is a tensor product rule. So let me write this tensor product rule in the case of SL2, and in fact, in other cases, it is, well, in fact, the definition of crystals is more complicated than in SL2 case, and the tensor product rule as well. But let me just give this example. So the tensor product of two things has to be just the Cartesian product of sets of vertices with the operators acting by the following rule. You see that this tensor product is not symmetric. So just flipping tensor factors doesn't preserve this oriented graph on the right. So, but on the other hand, the decomposition of tensor product in one order and of another order in the union of irreducibles, that is connected graphs, is the same in one order and another order. And there is a unique isomorphism taking one to another. And this is the commuter in this situation. And it can be checked that this commuter satisfies this property. So this is indeed a commuter. Now, so in fact, well, this is maybe some example of how this purely combinatorial definition works, but in fact, originally all this comes to Kashevara and Lustig, and they of course invented this because they studied representations of quantum groups UQ of G. And namely, they studied the limit of UQ of G modules when Q goes to 0. So there is no quantum group Q0 of G, of course, but there is a way of taking limits of finite dimensional modules over UQ of G in some way. Namely, you have to take canonical or so-called crystal bases, and then the action of appropriately renormalized Chevalier generators in these bases have a limit when q goes to 0, and this limit is monomial. That is, these operators are just taking basis vectors to either to basis vectors or to 0. So in the q to 0 limit, it is possible to monomialize the action. And moreover, so the next thing that of course our metrics, which is responsible for reversing tensor products, has both q and q inverse in its matrix elements. So it can have limit when q goes to 0, but if you renormalize it in the way similar to what I was writing here when defining the homomorphism of cactus group to the braid group, when you just make the permutations of two factors involutive just by brute force, by just dividing by square root of the braiding, then you get something well defined in the q to the 0 limit, and this actually defines the commuter on the tensor product of crystals. So now maybe let me formulate the main theorem. This was conjectured by Ettinghoff and several years after we who proved it with together with Eva Halacheva, Joel Kamnitzer, Alex Weeks, that the natural action of Cn on monodromy on the fibers of the equivariant covering of the Deligne-Mumford, of the real Deligne-Mumford space is equivalent to the Cn action on I'm sorry, on the tensor product, on the set of highest elements of the tensor product crystal. Of the given weight mean. So coming from the co-boundary category format. So these are irreducible G crystals corresponding to the highest weights lambda 1, lambda. So from the boundary. So let me, yeah. So this is the general theorem, and yeah, of course, it is still the question how much different is the image of this group from the whole Galois group. On the one hand, there are several examples where we see that the Galois group is strictly big, and in general, this is so. But there is some particularly nice example when G is SLN and all the lambda i's are just the first fundamental weights. That is, we consider the space of highest weight vectors of the weight mu in just the tensor product of standard representations of SLN, and we can assume that mu is a Young diagram, it's a partition of n. Then this space is by sure Weyl duality it is the same as the Specht module corresponding to mu. It is an irreducible representation of the group Sn. This is the Specht module for the group Sn, and its dimension is just the number of standard Young tableau of the shape mu. Now the Cactus group. So in this particular example, we have the action of the Cactus group on the set of all standard Young tableaux of the given shape. Yeah. So it can be described explicitly in well in combinatorial terms. You can generate the whole Cactus group by the involutions S1J for all J. And this S1J acts as follows. You take the Young tableau filled by, so this is the Young diagram filled by numbers from 1 to n, and you take the sub diagram filled by the numbers from 1 to j, from 1 up to j. This is some sub diagram, and this S1J is just a Schutzenberger involution of this sub diagram. I'm sorry, of the sub tableau. Formed by the boxes from 1 to j. So there is some explicit combinatorial definition of this action, and what we recently showed with Sophia Liao is that once if mu is not self-transpose, and mu is not a single hook, then the image of yes, Roma should be the pure Cactus group in the theorem, again in the same sense that there is a pure Cactus group action on this set, and there is it extends to the Cactus to the full Cactus group action if we consider the union of such sets for all permutations of them. So it can be described as the action of the group way. Yeah. So but in this example, all the lambdas are the same. So we have the action of the whole Cactus group on the same set. Then yeah. So if mu is not self-transposed and not a single hook, then the image of Cn in the permutation group of this set is at least the alternating group. So it is either the maximal possible or almost maximal possible, or there is this index 2 in the hook. So this means that in this case, the Galois group cannot be much bigger. So we cover almost the hook. Okay, so maybe it's time to stop here. So so please ask questions. Thank you very much.
Thank you.
Thank you.
Any questions?
I have a naive question. How much of this was, I mean, if you consider the Godin model and like formally forget about that, it is integrable, whatever, and just replace omega ij, the operator, with something, not omega ij, but deform it. How much of this, of what you just explained, basically relied on the explicit form of the Hamiltonian? I mean,
So yeah. So what I use here that the operators hi are have this form. So let me denote this by some formal symbols, where Tij satisfy the following property. They commute if all ij, k, l are different, and Tij commutes with the sum Tik plus Tjk. I'm assuming here that Tij equals Tji. So once we have these two properties, these operators pairwise commute. And we can.
And this kind of the condition that
this is the equivalent to the condition that the corresponding connection is flat. If you write d plus sum of Tij times d zi minus Cj over zi minus Cj. But this is flat if and only if these two relations. And this is all I need. So in fact, Aguirre-Felder and Veselov were dealing with this GIJ. So they didn't assume anything about operators represented.
What would change for XXX?
Yeah, so this is a good question, and I was planning to speak about this as well, but had no time for that. So yeah, so for XXX, XXX can be regarded as a multiplicative version of this. So we have some commuting operators parameterized by non-zero z1 zn. So they are all non-zero and pairwise different. Then we can play the similar game. So we can view these points z1 zn and as point on as different points on C star. And again, compactify the family of quantum integrable models to some some compactification, but which in this case appears to be M0 n plus 2 bar. And but what is the difference here is that there are at least two natural real forms related to this model, and each of them is well somewhat remarkable. So in fact, in this case, more interesting and maybe more natural because of generalization to other types, to not necessarily type A, is when I'm sorry, when how to say, when we assume that all the ZIs are on the unit circle, then what we get becomes something like toric model of toric version of the Dillon-Mumford compactification, and what we get as a fundamental group is the affine version of the Cactus group, and it is acting on the joint eigenlines for XXX hypotonians. And we have well, now maybe not a conjectural, not so conjectural description. Well, it is conjectural description, but in type A it is proof that the affine version of the Cactus group the monodromy action of this group on the joint eigenlines still can be described in terms of crystals. Well, it is well, it will involve some combinatorics, so it so to describe it, you have to define the analog of Schutzenberger involutions for any wild group. It is possible.
And what happened for XXZ? Because it's
well,
like XXZ.
For XXZ, we don't have anything like that. So the problem, yeah. So the problem with even with we even have this problem with XXX that there are in principle two sets of parameters. So there are inhomogeneity parameters and twist parameters. In one of them, the dependence on one of the sets of parameters is like difference, and on the other set of parameters it is still differential in the x6 model. And we can so what we can deal with is only the parameters the dependence on which is differential. In xxz model, all the parameters we can have behave as difference, not differential. So something special happens with when the difference of these parameters is like integer, or ratio is like the integer power of q or something. And this is the situation we still don't know how to handle. But when something special happens only when the parameters just coincide, we can play the more or less the same game.
Thank you. Any other questions? Maybe we should thank the speaker.